Hello. All right. Found an interesting book over here, The Mathematics of Artificial Intelligence by Gita Katuniak. It's a really interesting book. I have not read it fully yet, but there's really interesting things over here. And to review some of the stuffs, like definition of perceptrons, like a node artificial neuron, which weights W1 to Wn, bias B, and activation function rho. Then uh, the neuron is defined as the function f from r power n to r, given by the uh, summation of all the weights over all the inputs. So this is the dot product of the input vector and the weight vector minus bias b, and then this is fed into the activation function as the input. So cool stuff. Heaviside function rho x is 1 when x greater than 0, 0 when x less than equals to 0. Then we have the sigmoid function where rho x is 1 over 1 plus e to the power minus x. The ReLU, the popular ReLU function also here. And there are also like many of the cool definitions and examples in this book, like deep neural network of phi, a mapping from r to the power 4 to r with depth 5. So r to the power y r to the power 4, there are 4 inputs and 1 output, so that is r to the power 4 into r, and with depth 5, so there are 4 hidden layers. um, then application of DNNs, cool stuff. It's really interesting and lots of good for revision of materials. uh, Mathematical foundations for AI, expressivity, learning optimization, so training algorithms such as SGD, stochastic gradient descent, um, inverse problems, PDEs. Then it also like touches on optimization, why optimization and how the optimization, getting stuck into local minima, how to avoid getting stuck into local minima, gradient descent versus stochastic gradient descent, as it shows here in the landscape. Gradient descent goes down and gets stuck in a local minima, while stochastic gradient descent kind of backtracks a little bit and then goes back. And yeah, so ultimately SGD finds the global minima. This is really interesting. Also examples of generalization, overfitting. Like here is an example where it should supposed to be an elliptical function. Underfitting, the stars and green circles all like tried a linear separation, which actually did not work out. Then a circle, which should be the optimal solution, kind of optimal solution. All the stars inside and most of the green dots are outside, just a couple on the edge of the ellipse. Then you have the overfitting, so it's really interesting example. So during the overfitting, so in overfitting the decision boundary zigzags a lot to have 100% separation, but which is not ideal. And it also touches DC dimension and shows example with double descent curve, training error test, or how they're related, and interpolation point, and then the explainability of neural networks. It also talks about the inverse problem. So given an ill-posed inverse problem, Kf equals to G. Then from there we want to find the inverse. And then of course the partial differential equations. Then in conclusion, 7 mathematical key problems. Let us conclude with 7 mathematical key problems of artificial intelligence as they were stated in 6. So, 7 questions are: what is the role of depth? So, how many hidden layers and why so many hidden layers? Number 2, which aspects of a neural network architecture affect the performance of deep learning? Number 3, why does stochastic gradient descent converge to good local minima despite the non-convexity of the problem? Number 4, why do large neural networks not overfit? Number 5, why do neural networks perform well in very high dimensional environments? Number 6, which features of data are learned by deep architectures? Number 7, are neural networks capable of replacing highly specialized numerical algorithms in natural sciences? Alright, so this is a good interesting paper based on an invited lecture at the International Congress of Mathematicians 2022. So it's pretty cool to refresh, revise principles, mathematical principles behind neural networks. So I'll post the link for the paper, for the book in the description.